AP-style normal curve problems using the central limit theorem, as well as problems that don't require the central limit theorem. So let's say Bob sings songs. Good for Bob. His average song lasts 3.2 minutes with a standard deviation of 0.6 minutes. Let's assume the song lengths are normally distributed. So assuming normally distributed means that the population of all the song lengths follows the standard normal curve, a nice perfect normal curve. What is the probability that Bob's next song is more than 4 minutes long? Well, it says we are normally distributed, so we're going to draw ourselves a quick little normal curve. And we have our markers at 0 and -1 and +1 standard deviations and so forth. And let's go ahead and convert 4 minutes into a z-score so we can do some normal curve calculations. The average is 3.2, so we want to figure out how far above average we are. 4 minus 3.2 is going to be 0.8, and then we divide it by standard deviation so that we can figure out how many standard deviations we are above average. So divided by 0.6, plug that in your calculator, and you're going to get 1.33 rounded off here. And so our z-score is 1.33. We want to know the probability that Bob's next song is more than that z-score. So on our normal curve, we would plot something like that, and we would shade above that value. Now to find the area above a certain value, our left end has a z-score of 1.33, and our right end has a z-score of positive infinity, which for our calculator I'm going to call 99. That's going to be close enough. So we take out the calculator and we do second distor for our distributions, normal CDF, and my lower bound, my left side, is 1.33, and throw in an extra 3 there because it's 3 repeating. My right side is 99, and when I calculate that, it's going to give me an area of 0.091. So 0.091 is the area under there. It also is the probability that Bob's next song is more than 4 minutes long. So 0.091 is the answer to the original question. Next question says, what is probably that the average of 5 random songs of Bob's is more than 4 minutes long? Now there's only one thing that changes here. We have a normal distribution, but we're taking an average of 5, and the distribution of averages of size 5 is also going to be normally distributed, but it's going to be a narrower curve. And how do we find the standard deviation of this sample average? What we would do is take our original standard deviation, our 0.6, and divide it by the square root of 5, because that is our sample size right here, 5. And when we do that, we get, let's see, 0.268. So we'll use that value there as our new standard deviation. Then we repeat the problem exactly like we did it before, which is to say 4 is how far above average? Well, 4 is, if we subtract our average of 3.2, it's again 0.8 above average. The difference is when we figure out how many standard deviations above average, we don't use the 0.6 that we had before. We use the new standard deviation that we just calculated, since this is an average of 5 random songs. So we divide it by 0.268. And in my calculator, I'm going to do this in one step. I'm going to do, I know that 4 minus 3.2 is 0.8. I'm going to divide it by my answer, so I don't need to re-round values that are already in my calculator. And when I do this, I get 2.98. So my z-score that I'm starting from is much higher, or more importantly, farther away from 0 than the previous problem. So on my curve, I'm looking for a very small tail here, starting at 2.98 and going onwards to a value that is higher, more, so we'll call it 99. I do my normal CDF, 2.98 to 99. Let me fix that. So if you make a mistake, you can always hit second enter and go back and edit your value. It is 2.98. And that gives me a probability of 0.00144. So 0.001 is the probability of being above that z-score, which is the probability that an average of 5 songs of Bob's is more than 4 minutes long. Now, it seems weird that before we had about a 9% chance and here we have a 0.1% chance. The reason for such a huge discrepancy is a song that is more than 4 minutes long in this collection is actually a pretty long song. It's not all that common. It only comes up 10% of the time. Is it going to be more likely or less likely that you take 5 songs on average, or 5 songs from the distribution randomly, and you average them together? It seems unlikely that you're going to get 5 of them that are all in this top part of the curve. And in fact, it's so unlikely to happen that that's why our probability here is 0.001. It could happen, it absolutely could happen that you'd get an average that high, but it's just very unlikely. Next example, we have good old Mary here, and she eats cabbage. On average, which almost rhymes with cabbage, she eats 4.5 ounces per meal with a standard deviation of 0.8. So there's our values that we're looking for. Let's assume that her meal weights form a nasty bimodal distribution. So for whatever reason, the amount she eats is either very low or very high. So we have some kind of bimodal graph, and I'll make that a little darker. So let's assume that the graph is not very clean to start with. First question asks, what is the probability that a random meal of Mary's will have more than 4.7 ounces of cabbage? Well, if we had a nice perfect normal curve, we would go through and find our z-score and then figure out where in the graph it is and shade our graph and do some calculations in our normal CDF, and we would answer the question. The problem is it says that the meal weight population forms a nasty bimodal distribution, not a nice normal curve. So we cannot do any calculations for this problem. The reason we can't find anything is we can't make predictions from the description a nasty bimodal distribution. We can make predictions from normal curves, we can make predictions from some other distributions, but not this. So there's really nothing we can do to answer that question. However, the second one here says, what is the probability that an average of 50 random cabbage meals of Mary's weighs more than 4.7 ounces? Well, the nice thing about the number 50 is that it can turn any distribution, including this ugly mess right here, into a nice, smooth, clean, textbook normal curve. And so we're going to take advantage of that property and use the normal distribution to model the sampling of an average of 50 random cabbage meals. So let's go ahead and find what our new standard deviation is going to be. Our old one was 0.8. So our new standard deviation of the sample means of 50 is going to be our old standard deviation of the whole population divided by square root of our sample size. So divided by square root of 50. And if we pop that into our calculator, 0.8 divided by the square root of 50, we're going to get 0.113. 0.113 is our new standard deviation. Now, we still from here can assume a normal curve because we have that big enough sample size. So I'll sketch my normal curve, and we need to then find a z-score. So we want to know the probability that Mary's meals weigh more than 4.7 ounces on average. Well, 4.7 ounces is above the 4.5 average. So 4.7 minus the 4.5 is going to be 0.2 ounces above average. Now that 0.2 we divide not by our old standard deviation but by our new one here, divided by 0.113. And so 0.2 divided by that answer right there, we can do in our calculator. And I can use that second answer function to reuse that value. And I get 1.768 if we round that off, or 1.77. So that is our z-score. So we want to know the probability of having that or more, a z-score of 1.77 or higher. So I'm going to shade that on my little graph here. And we're going to do our normal CDF trick, starting from here and going up to positive infinity. Let's go ahead and start with this value, start with our answer, and then go up to positive infinity, which I'll use 99 for. And I get probability of 0.03, and we'll round that up to 9. So probability of 0.039. And that is the probability that the average of 50 random cabbage meals of Mary's is going to weigh more than 4.7 ounces. So this here is the answer to the original question. We couldn't answer this first one because we had this bimodal distribution, but because we had 50, a sample of 50, that's always going to smooth out a perfect normal curve. That's a big enough sample size to do that, and so we can answer this question using our new standard deviation.